Hi, everybody. My name is Jonah Crocker. I'm an intern for Mile High Flood District and a student at CSU working on my Master's of Natural Resources Stewardship with a concentration in ecological restoration. Please join me in welcoming Bruce Rindahl, our flood warning manager, to discuss the future of forecasting.
Thank you, Jonah. As you said, I'm Bruce Rindahl, the flood warning manager for the district. I've been in this position for about 2 years. Just to show I have credibility, there will be a flood today on Cherry Creek this afternoon. So, what do we do about flood forecasting? Where are we moving with it? I like to say, do what you can with what you have. So, what we want to talk about in the flooding is, can we really forecast floods? What do we have? What are we showing? Can we forecast it? Can we do information about it? What can we do to validate it, verify the information? This is how we want to take a look at what we have to do for floods. So, we are facing a crisis in the district. By the numbers, we need to take a look at all of our effective hydrology studies and all our information, but those quickly add up. For instance, we have, over 300 actual hydrology models. We have, say, 150 of them are effective. Then let's say we've got to run 7 design storms for each one of those models. We've got to do impervious and existing and future impervious percentages. We've got to do, 3 climate change scenarios. And that comes out with some other scenarios, and that comes out to how many runs are we talking about?
19,152 runs.
There you go. Well, let's say they have to do it about 51 minutes per run. How many hours is that to run?
16,297 hours.
In days?
678 days.
Years?
1.86 years.
So we've got almost 2 years of computer time to run these scenarios. That's an awful lot. So we need to find some way to make it faster. Come on. So the first thing we run into is Excel is very, very slow. Now there's a reason for that. It does a lot of other things. It does color coding, it does scenarios, it does other graphing built in, and a lot of other things. It calculates all the cells as you're going through, and it's very, very slow at doing that because it's not designed to do all that. So what we want to do is to take a different look at how we can compute our hydrology models to make them very fast, make them near real time, and put them in a scenario. So we do something called do it all in the database. Now, for those of you whose eyes are glazing over right now, or rolling, either one, that's fine. What you're seeing here is a printout of a table in our database that has every parameter that we need in COHP. We're talking length to centroid, length, slope, area, imperviousness, infiltration rates, initial, final, and decay rates. They're all there. They're all stored. And we can manipulate and calculate those directly in the database. In addition, we also have the GIS boundaries of all the subbasins for your models. So we can actually distribute rain, we can do any assumptions we want, we can put NOAA Atlas 14 numbers on them, we can put historic rain, we can put anything we want so they're geo-referenced and we can kind of take a look at what's going on. Now, down the road, we're giving you a little warning. We're going to be kind of really onerous about we need the files from your models and they need to be correct GIS and they need to be the right subbasin because we can then do magic once we have them in this location. So, how do we speed up COHP? We've got all the numbers in the database. We want to do everything else in there, so we want to try and figure out where are the pain points in calculating. First one is Horton's equation. It's an infiltration equation. And for those of you computer geeks like I am, this exponential function is very, very painful to compute. It takes a long time. So we want to figure out a way to do that. Well, currently COHP computes it twice, takes the average, and says that's close enough. It's close enough for government work. Now, what if we could actually go in there, remember our high school or freshman calculus, integrate this thing, we would get an exact answer. And we would also get something magic that says you don't even have to do it twice. You can do it one spot in that interval and you will get the correct answer. So now we are taking a look at getting half the number of calculations performed. And remember, there's a lot of those calculations. It's done every time step for every subbasin. So if we cut that in half, we do a lot of reduction of calculations. The next thing we want to look at is the unit hydrograph. Now, for those of you who didn't have worked with this, COHP works through and comes up with 5 points on this unit hydrograph curve. And it says, once those are fixed, then we have to fit a curve through those. Now, you might ask yourself, how does COHP draw a curve between those 5 points?
Initially, the COHP solves for a third-order polynomial connecting T0 and T2. If the polynomial is less than 0 for any point between T0 and T2, the method switches to a second-order polynomial between T0 and T1, and a linear equation between T1 and T2. The COHP then attempts to fit a third-order polynomial between T2 and T4. If no suitable third-order polynomial can be found between T2 and T4, the COHP attempts to fit 2 second-order polynomials, one between T2 and T3, and one between T3 and T4. The COHP always selects a linear equation between points T4 and T5.
Yes, folks, it actually says that. This is straight from the manual. And thank you from the God of COHP of how to do that. So what's a better way? Well, what if we just put 4 curves on them? Second order said they've got to all match up. They have to, the slopes or derivative have to match up, and it's got to be level at the peak. That's what we call a spline. And it sounds weird that we're now doing 4 curves with 3 unknowns. That's 12 unknowns. But we have all those other equations, and now we have 12 equations, 12 unknowns. Which sounds a lot to you, but for our computers, it goes, hold my beer. Knocks it right out, and we have a unit hydrograph for all of them. We can even integrate them so all the other steps are done very fast. Now, the next step, and this is again from our manual, is if you don't use a 1-minute time step, maybe your unit hydrograph can be off. Again, this graph is from the COHP manual, and you miss the peak, and that can be quite intensive and difficult for us to work with. So what do? We just shift the scale a little bit. Slide it over, say it's good enough, we'll just kind of rescale it, and that guarantees that your unit hydrograph on 5-minute time steps will hit your peak, and it will get you the value. Now, this also knocks your computing time down by a factor of 5, so you don't have to go to a 1-minute time step. Again, we're looking for speed here. So what have we accomplished by doing all these steps? Remember, about 51 minutes for a computation. I can't read these numbers, but the bottom line is you put the various steps. You load the basin parameters, you load the precip, you load all the other information, you run the impervious percentage, you do the effective precipitation, you compute the unit hydrographs, you spit it out in a format that's ready to run COHP, 16 seconds. That's a bit of a performance improvement over the 51 minutes we have. Plus, they're already integrated. We go right into the swim models and run them that way. So now that we have those online and ready to go, we can take a look at what we can do with the models. So let's do a historic simulation. Let's take a look at Lena Gulch. We put the rainfall in for June 21st of last year, run all the models. 16 seconds later, we get the results. Nothing. Now, as a hydrologist, I love this. It was great. Why? It didn't rain on the 21st of June. We had 0 rain. Coming up, when you see AIs are going to be doing hydrology models for you, that's the first question you ask. If it doesn't rain, what happens? And it better be nothing else came out. So what we need to do is validate our models. If zero rain comes in, what happens? Do you have error checking? Do things crash because you have division by zero? All this other information has to go in. So how good are your models? They're as good as your precip estimate. Trust me, you can do some of this stuff with a rational method model. If your precip is close to what's actually going to happen, you're going to be dead on. So let's actually put something interesting in. How about the 22nd of June last year? And that's when we had almost 2 inches of rain in some part of the basin. We'll rerun everything else. Magic, 16 seconds later, boom. We get over 1.5 foot of flow over Maple Grove Reservoir Spillway. We get an outflow of about 700 CFS. And that pretty well matches up within 1/10 of a foot of what actually happened. This is the outflow, this is the spillway from Maple Grove Reservoir on that date. Now, some of the other tools that come with this, it can actually take a look at every process in the swim model, store it, and we can put it on a web page. And you can point at it, look at it on a web browser, point it at a certain spot. Remember when I said it was about 600 or 700 CFS coming out? According to the swim model, it's 699.32. But the point is you can look at any one of these parameters, any location, and it shows you what the models will do, and it'll be instantly available. So now, Bruce, this is forecasting. Where's the forecast? So we've done the framework that makes it incredibly fast. We can use design storm information. We can use historic information, or we can use forecasted rainfall. And again, put through the same process, run it automatically to schedule. I don't have to wake up at 6 o'clock in the morning or 10 o'clock in the morning on a Sunday and say run and output it. We can just do it as a generated schedule and go from there. Where do we get our forecasts? We have a company called Hydromet Consulting. It's developing 5-minute rainfall totals for us. Every day on a high threat day, we can find out what the potential forecast is, ingest that automatically, and put it into our models. And this was forecast yesterday when I put the slide together. Not much happened because there was not much rain. So it worked beautifully. We showed how it's going to increase. We showed how the forecast can be. Then we can integrate it in our displays with all our other models that we want to do. So what is next? Obviously, we've proven the concept. We've taken the models, we've run them fast, we've compared historic storms, we're now putting forecasted rainfall in, and we want to do this automatically and put them into the models that we have. First up, I hope, westerly, upper and lower, because we have no models in there, and large regional detention ponds. Lena Gulch, Goldsmith Gulch for comparison of the ones we have. So hopefully online, in the next week or two, these will be part of the displays that we're running, and we'll be doing it fully automatically. So I want to thank you all for being here. Appreciate the sources from the criteria manual and other information, all the people that helped out. And if you want any information, go to milehighflooddistrict.org, and we will work with you on demonstrating them. Thank you very much.